So let's take a look at our print and see what is the difference between the previous incarnation, the XZ class, versus this class. You should have gotten a copy of these with the registration packet, but let's talk about them. Here we have a front and a side view. This is our straight two-axis part that we did in the previous class, and we've added 1/4 inch by 1/4 inch holes at the quadrants on the OD of the part. We've added 4 632 holes that are 1/2 inch deep, and we've also added a milled hex across the front of the part. So these are going to be the focus of the C-axis class, and I think they're a good representation on what is possible without having a Y-axis, but being able to use milling. So let's look at some of the processes that we'll be using. We do have the live milling face cycle that we'll go into in depth. We also have a live face drilling can cycle that should be in the packet you got sent, as well as the live tap. Whoops, that one's a little busy. There we go. The live tap face cycle. So we'll go over all of those as we need them, but let's focus on what we need to do now to make our machine ready for this advanced part. Okay, so we're right back at our machine. I'm going to go ahead and take a peek inside the front door of the machine so that you can see we have the tools that were remaining from our two-axis part, but we've added an X-axis drill for the 4 quadrant holes. We've also added a live Z-axis end mill, as well as the drill and the tap. As we previously mentioned in the two-axis class, I've grouped like tools on their respective sides of the turret. As you can tell, now that we have Z-axis working tools right next to X-axis working tools, we could have some interference issues. So I made sure that since I did not have the ability to skip a pocket, skip a turret station in between these two tools, I just positioned the shortest available Z-axis working tool to position next to the stick tool. This should prevent this tool from contacting the jaws as they're spinning. So I populated my turret with these new tools. Most of them, there's our tap. Most of them are not going to require anything for the nose comp section. If they're a drill or tap, obviously we don't have any compensation factor to be used. However, when we get down to tool number 9, which by looking at our tool list, you see that station number 9 is our live Z-axis 1/2 inch end mill, we are going to want to be able to comp that tool. And I also don't have the benefit of a cam system that will automatically compensate for the diameter of the tool. So to ease my programming, I'm putting the full radius value of this cutter in the nose comp column. So on 9, which is, as we already talked about, the 1/2 inch end mill, put a 1/4 inch in both the X and the Z column. And previously, when we did nose radius compensation, we had a P value here to represent 3 for a turning tool, 2 for a boring bar. For an end mill, we're compensating from the center of that tool. So our P value for an end mill could be either 0 or 9. They both mean the same thing. They both mean we're compensating from the center tip of the tool. And our side action drill, it's just a drill. We don't need any compensation for that. So now everybody is all set in terms of the tools. I do want to stress, let's go back to looking inside the machine. I do want to stress that these tools, we want to be gauged from the center, the X0 on these tools. We want to have absolutely right in the center of the tool. If you don't do that, particularly on the end mill, you will find that our tool path will not be correct. Our flats won't be straight across because the machine is utilizing the tool center line as the the offset for the part. So worst case scenario, if you don't already know what the X0 is for one of your live tools, feel free to touch the OD of the tool off of your presetter to get an initial value, and then make sure that you subtract if you touched on the OD side of the setter, or add if you touched on the ID side, the entire diameter of the cutter. Why isn't it going to be the radius of the cutter if we're just moving to the center? X-axis is always in a diametrical value until we turn on a milling can cycle. So if you are going to touch this off the OD of the part or off of your presetter, make sure that once you have the calibrated value, you add or subtract the entire diameter of the cutter, and that will put your X0 center line at least close to where it should be. And then once we have a result from the part, we can adjust from there. Also, before I forget to mention it to you, the biggest mistake that I see people making when they're milling in C-axis, you measure your part and you find that you need to adjust your offset ever so slightly. With every other tool in the world, you're using the X offset value to adjust. Don't do that when you're milling. Adjust here at the nose radius compensation value. So if you find that your hex is 5 thousandths oversized, you'll put the minus value in the X and the Z column instead of where you normally put it with a turning tool, which would be the offset column. There was one other thing I wanted to mention. Okuma offers what they call negative tool radius compensation as an option for most machines. We've gotten to the point these days where most of the sales guys they know that this is an important value, and so they'll add it to the machine automatically. But the negative radius compensation value is, let's say for instance, we utilized a CAM system to generate our code, and so the CAM system automatically built in the compensation for the diameter of the tool or the radius of the tool. If that is the case, and all of a sudden I find that I have to minimize I have to reduce the size of my hex by, let's say, 5 thousandths, I had to go negative on that value. If you do not have the tool nose or the negative tool compensation option on your machine, this will actually make the part larger. Yeah, a little bizarre, huh? So negative compensation is an option, and if you find that you're fighting and you can't seem to get the machine to make the part smaller by putting a negative value in there, give your sales guy a call and find out whether or not you have the negative comp option, and if you don't, you can always get it field installed. That is the rationale behind this is that Okuma expects you to do this, which is put in the radius of the cutter in your nose comp column, and by using that as a philosophy, there is no negative tool. If you don't have a tool, it's zero, but anything negative means that there's no tool in there. And by doing this, you have the ability to make the thing smaller or larger. Confusing, right? Anyway, now we've done all the preliminary that we need to do with our machine, so let's move on to our program. In our 2-axis class, we covered several of the editing features that Okuma gives us on the machine. So in keeping with that, let's use a couple more of the tools that Okuma has built into their control. Right here, I have the 2-axis program that we used for the class. I don't want to overwrite that because more people will be coming through this class in the future. But I would like to have all of the 2-axis code available to me. So I'm going to make a copy of this so that my source code, my original, will still be intact, but I can add to it for the class. So by highlighting the individual file name, I have a button here for copy. by pushing F5 copy, it gives me the opportunity to change the name, which is of course something I want to do. In this case, I don't want to overwrite the original. We'll call this XZC class. And as I mentioned in the 2-axis class, one of the biggest mistakes people make when they're creating a program or copying it over is they type in the new name. Once they get done with it, they get all jolly and they hit MD1 copy, or they try to finalize this copying process without touching the input key. I have to hit enter, which takes the code from the input buffer and puts it into the file name. If you don't do that, it's going to try to copy over with the existing name, but of course that program already exists. So now it's asking me, where do I want to copy it? I could copy it to one of my USB drives if I chose, or the terminal connection, which is an Ethernet connection from your machine to the Office network. But in our case, we want to drop it into the machine directory 1, or MD1. So as soon as I touch it, it creates the new program with all of the existing text from the previous 2-axis class. And so we're just going to drop down to where we want to start inserting code, and we will believe it's right there. Yeah, right before the cutoff. And now just so that I don't get lost as to where I'm adding text, I just added a bunch of lines here so it'll make it easy for me to jump right in and start creating the new code. There's another feature that we didn't talk about during the C-axis, or the XZ class. If I wanted to save this, I've just made changes. I want to save it, but I want to keep editing. And the impulse is just to hit quit stop. It'll ask you if you want to save. You say yes, but now you have to go back in and open that same program. There's a little 2-step process there. That's not wrong. You can certainly do it anytime you want, but if I wanted to save this program and continue editing, I could arrow over, and now I've got a save button. So I'll just tap that. I have the opportunity to change the name if I want to. I do not, so I'll just hit OK. It asks me if I want to overwrite. Yes, I do. And now I've saved all my changes, and I can continue on with my editing. This is also very handy if you make a mistake. There, I just made a mistake. I've got a whole bunch of gibberish on here, and if I think, oh geez, I didn't want to do that, I can always quit stop. Do you want to save? No, I don't. So now I've dumped those editing features, those edited features, which is just one more reason why I like the save button, because once I have added a block, if I'm happy with that code but I want to resurrect my undo, I will tap the save button and save the program. All right, so let's move on. Before we start any of our live tool drilling cycles, I'd like to show you a parameter that we're going to want to make sure is set properly on everybody's machine. So if you reach up and touch your parameter button that's on the machine control, it'll pop up with the common variable page. That's perfectly normal. We want to do F8 display change, and we're looking for the parameter that's labeled multiple machining. Again, I've done this a couple of times in some of the other classes, but let's make sure if you don't see multiple machining here, use the arrow right button while the display change screen is up, touch menu change, and make sure there's a check mark in all display. That will make sure that your multiple machining is showing. And when I touch it and hit close, now these are the parameters that relate to all of the live drilling cycles. And the one I want to address is the multi-cycle return point. What this is, it's the default value for the machine to return the tool prior to indexing to a subsequent hole. Wow, that's confusing as all get out. Basically, it's where to put the tool after you're done drilling before moving on to the next hole. And in general, the factory likes to send these things out with the parameter set to cutting start point, which means if my tool is delivered to a 1/4 inch in front of the part, and that's where we execute the drilling cycle. However, we say, hey, the tool's not going to be touching material until it gets to Z minus 120. This parameter set to cutting start point will only pull the tool out of the hole and then index to the next feature, which is a little scary if you're inside a counter bore or something that you have to retract out of in order to not break the tool during indexing. So I suggest to everybody that when you get your machine and you start playing around with it, go to display, change in parameters, find your multiple machining, and we will set the multi-cycle return point by touching F1 menu and change it to cycle start point. What this is going to do is, regardless of where the tool touches material, it will always return that tool to the initial point. Where was the tool delivered prior to calling the cycle? So in the example I just gave, where we delivered the tool to Z positive 0.25, but we didn't start cutting till minus 120, this means that after the first hole, it will make sure the tool comes back to positive 0.25 before indexing to the next hole. That can save you a world of hurt. Once that's set one time, you never have to deal with it again. It's a modal thing. Just check it, and you will avoid some broken drills. All right, so let's take a look at our 3-axis process plan. See exactly what we're going to do first. So all of these operations from 1 to 8 were already completed in our 2-axis class. Looks like we're moving on to the face drill. Let's take a look at our print so that we can see exactly what we need. It appears that we've got 4 holes. They're on a 1-inch bolt circle and they're 1/2 inch deep, but we are going to keep in mind that they are going on this face that's 120 thousandths from our Z0. So we'll pay attention to that as we start to program the depth. All right, so our first live tool call, we're going to use pretty much the same structure that we used previously. We're going to start with a sequence just like we always did, and since we're using tool number 6 as our 110 thousandths diameter live Z drill, we'll start with N6. Get the cursor out of the way there. And in keeping with our format, we'll throw in the G0 because we know we want to be in positioning mode no matter what and cancel any cycles that are currently active. Previously, we were using G95 inches per revolution programming. However, now that we're using live tools, we want to use G94 for inches per minute programming. And then I always add in an M5, mainly because I did not turn off the spindle, the main spindle from the turning evolution that happened before. And by doing it now, then the machine is in a status to be able to activate C-axis mode. If the spindle's rotating when you command the C-axis M code, it will generate an alarm. On our next line, we will repeat the process we did before of saying another sequence number just in case you have the tool restart feature on your machine. And then we will call up tool 6, offset 6, and since this is a drill and we're not worried about radius compensation, we don't need the first 2 digits. We'll just call up the first 2 as being the turret position, the second 2 being the XZ offset. And because I like to be nice and clean, we're going to put in a word description of what this is, live drill. And I like to put in a size as well, just in case I have to send somebody over to replace a tool for me. They can see just by looking at the program exactly what size the individual drill is. And then we'll turn on our coolant. Now on our previous statements, let's take a look. Right after the tool call, we have a positioning move. But we put that in on a standard turning cycle because the spindle was already rotating. That's not the case in the live tool. We've got it turned off. And this is probably one of the more dangerous times when proving out a program is when the tool is positioning from its turret safe position too close to the part. And I always like to have the spindle rotating during this time, just in case there's a slight bump. There's a less opportunity for damage to the live tool if it's rotating when something nasty happens. So we're not going to move the tool just yet. We're going to enable the C-axis mode through M110. And in case you forget that, we'll call up our 3-axis M codes, and right down here at the bottom, M110 C-axis connect. That's on a line all by itself in my format, but now I am ready to fire up the live tool. And let's call up that M code list again so that you can see M12, 13, and 14 are my live tooling spindle activation codes. So we're going to do M13 for spindle clockwise. And now I'm going to have to give it a speed, but here we're going to do something a little different. When we did the main spindle, it was say S4000. Oops, that's a 5000, Charlie. S4000. Well, Okuma doesn't want us to mistake turning on the live tool with turning on the main spindle. On this particular machine, I have 6,000 RPM available for the live tool, and I don't want to accidentally put in S6000 and have the main spindle go. So they've changed the code up a little bit for the live tool. Instead of being M13 S4000, it is M13 SB equals. That stands for spindle B equals 4,000 RPM. So any live tooling Okuma machine is going to use SB equals as rotating the tool instead of rotating the part. So that's a good one to keep in your data banks. Now that we've got the spindle rotating, now I feel free making my motion to X 1.0 Z, let's go to say a 1/4 inch from the face of the part, and at the same time I'm going to orient the C-axis so that the tool is ready to go to its first hole. Now I chose going to X 1 inch simply because that's where the hole is going to be drilled, and so there's no real reason to go to an X clearance plane, particularly since this Z is a 1/4 inch away, and that should make everybody comfortable as the tool is rapiding down to the face of the part. Okay, so now we're in position and we've got our spindle rotating. I'm ready to look up what my my cycle is. And from my G-code list, you'll see that it's G183. So I'm going to grab my G183 cycle document, and it's in the same format as the ones we used in 2-axis, where it tells me, okay, move to the tool clearance plane or home position, tool and cutting position, shift into milling mode, yes, yes, yes. We've done it all. And then we're going to call the cycle, G183, with some codes. And here is the explanation of the G183 cycle that's taken right out of the manual. Very similar to the G73 and G74 that we did in the 2-axis program, we have the ability to do a combination of short retract and long retract. So it's basically a combination of 2 cycles into one. And our format, let's go ahead and key in G183 as our specific cycle. And I do have to repeat where the X is. Even though I'm already sitting at that position, I do need to repeat it so that the machine is clear that this is truly where we're doing this is the diameter of our bolt circle. So I have my X, now I want my Z in there. And the Z on this particular part, let's take a look. We know that, where is it? There we go. We know that it's 1/2 inch deep, but we're 120 thousandths already into the part. So my minimum thread depth from Z0 is going to be minus 620? There we go. So I want to make sure I drill beyond that. Let's give it 100 thousandths of drill tip clearance so that our tap will do very well when it goes to the bottom. And we'll give it a C0 because that's where we're currently located. Now our K value. This one takes me a little bit to explain to customers, but the K value is expressing where the tip of the tool is right now in relation to where the cycle is going to start. So let's call back up our G83, and hopefully they show us, there we go, right there. Q2, or the K value, is an absolute, I'm sorry, it's an incremental but positive value from where the tool is now to the top of the material. So we know that our material is 120 thousandths below the zero, and we're a quarter up from the top. So if I wanted to just start pecking from the 250 and I didn't care about the air, I'd call it K0, because that would just start pecking at my increment from where the tool is now. However, I want to save myself a little bit of time, so what I'm going to do is I'm going to put in a K value that causes the cycle to start something below where we are now. And let's just say we're going to go K point, let's go 250 and then 120, so it's 3. Let's just say that K250. So it's going to start pecking at our Z0, and we'll have an opportunity to see how it functions before it actually makes contact with the part. And next we're going to do the L value, which, as you see here, the L value is the depth in between retracts. So let's just give that an L of 0.25, and our actual amount of bite per peck, let's give it a little different value. So now it's going to do 100 thousandths per bite, but it's going to do a full retract after every quarter of an inch. And the last is a feed rate, F20, let's go 20 inches a minute. There is a provision in this can cycle which will allow us to do a number of holes, but I'm not going to use that right this second. I'm going to show you the longhand method. We know that a canned cycle is what they consider modal. So until we cancel that cycle, every position that we specify after this initial call will repeat these exact parameters. So I have my hole at C0. Let's make another at C90, another at C180, and another at C270. Now that'll be all 4 of my holes, and to cancel the cycle, I'll use G180. And then I like to put in a rapid to a clearance plane just so the thing will move away from my part and not scare me to death. Make sure that you put in the M12 to turn off the spindle. I could also, if I wanted to, I could put that on the same line as the motion. Just doesn't matter, but it's a matter of preference. And then I will cancel the live tooling, the C-axis connect mode. You don't have to do this if the subsequent tool is also going to be a live tool. However, it can cause problems when you're trying to restart. Are you in C-axis mode? Are you not in C-axis mode? It becomes confusing. So I like to turn it on, use it, and then turn it back off. Now our motion to home will be the same as it's always been. X30 Z10, and an optional stop so that we can pause the machine if we're proving out the program. It won't just continue on. So let's take a look and see how we did. We will select that, and now we'll go to our back to our main operating screen. Make sure we're looking at the graphics, and we'll do a skip to get forward, get through the 2-axis turning. We'll skip right to our next tool. Once again, I'm going to go for the large screen of the animated simulation so that we can see what's going on. We'll turn on our program so that we can see it. Now we'll use the restart. We'll select N6 because that's tool number 6. Make sure that I turn on my 3D graphic during drawing and press OK. So now we're zipping through the 2-axis stuff that we did previously, and when it gets to my drill, it will pause, waiting for me to push sequence restart. Now I'm going to get rid of the trace lines just because right now it's a little busy, but keep in mind that if you want to see the difference between a rapid move and a feed move, the trace animate is a really good one to do that. So we'll hit our sequence restart. It has now positioned the turret and the machine in a condition that it would have been in if we had run the program normally up to this point. And now we can press the cycle start button, and here comes our drill, doing the combination of short retract and long retract and drilling our holes. Now some of you may have noticed that, hey, wait a second, what's going on here? Even though we commanded C-axis motion, the graphic was showing us moving the tool. Well, the reason behind that is because the software for the graphics will never move the part. It'll move the tool, but the machine itself will be moving the part around. So to display that, I'm going to go over to my collision avoidance page, and let's see if we can get a good angle here. Move this over and do that'll probably be okay. We may have to do a little bit of a, there we go. We'll give it a bit of an isometric view there so that we don't get our vision blocked by what's going on. And now we'll do our cycle start. Now we'll do a little super speed action. Okay, so now we're ready to see this. Our part is complete for 2 axis, and now we'll hit cycle start. Now you'll notice that instead of moving the tool around, the machine is behaving as it actually will, rotating the spindle. However, the special function graphics, again, just it will never move the part, so we just understand that the C-axis is moving, not the X. So let's take a look, and I believe we are happy with the Z-axis live drilling portion. So now we can move on to the next process, which will be tapping. So now let's go back and take another look at our process sheet, see what comes next. Looks like we're doing the face tap action. Let's get back in here and edit our program. Because the G184 or live rigid tap cycle is so similar to the Z-axis drill, we could literally copy this entire thing over, change this to a G184, modify a couple of our values here in the cycle line, and be done with it. But I'd like to take this opportunity to show you a couple of different options that are available. So just as I mentioned, I am going to copy everything, but once we paste it, we're going to make some changes. There we go. Obviously, the first change should be to change our tool, which in this case we've decided our tool number is 5 and 5, and once again no radial compensation, so 4-digit number is just fine. We'll call this the live 632 tap, and we still do our M110, and 4000 is going to be way too much for the A cell D cell to keep up with the inertia of the machine. So let's knock this down and call it 250 RPM. We can probably do more than that, but let's keep it light for right now. And our motion can still be exactly the same. We're going to start by talking about G184. Okay, so this is a point of confusion with an awful lot of Okuma owners. If you look in the manual, you'll see that there are 2 face tapping cycles, G178 and G184. And it's like, well, why do you have 2 of them? Well, the machine is designed to have one cycle for rigid tapping and a second cycle for floating tapping. And the factory has designated 178 for the rigid tap and 184 for the floating tap. However, they realize that we like to associate anything that ends in 84 on a G code with a tapping cycle. So I'd like to show everybody a real quick parameter that we're going to want to check on your machine before you decide which code to use. So by touching the parameter button, going to F8 display change, you're probably well familiar with this sort of thing. And we'll come over to the optional parameter multiple machining. If that's not visible, you can always arrow over to your menu change and make sure that all display is selected. But once you pick up multiple machine, you can close this, and you notice that item number 6, G184, G298 tapping mode, can be set to either floating or concurrent. The factory will send the machine with this as a floating tap, and if you intend to use 184 as a rigid tap, definitely change it over to concurrent so that now 178 and 184 will both be rigid tap cycles. The question comes up usually when I explain this to customers: why would you need a special cycle for a floating tap? Isn't it exactly the same as a rigid tap? And my answer is, yep, I don't know. Somebody who's well above my pay grade thought of that. But I always, right off the bat, will change everyone's machine to rigid tap for G184. And, if you've got a floating holder in there, so what? Whoop-de-dee, it's still going to do exactly the same thing. But by flipping that parameter, now you can use either of those codes. All right, we chose to use G184 for this, and I am going to delete the additional holes so that you guys can see a little something special here. In our G184 line, we're still going to have our X. Our Z, we're going to knock that down because we don't need to go as deep as the drill. Otherwise, we're going to bottom out that tap. We still have our C action, speak Charlie. We still have our C right there, and we have our K that's the same. We don't need the L value, but we do want we want a feed rate, and in our case, that feed rate, we're going to make 1 divided by threads per inch multiplied by the spindle RPM. So in this case, that's 7.8125. It's 1 divided by 32 multiplied by 250. There's our feed rate. And the last value that I want to put in here to show you a little time saver is if you put a Q value in there. That Q is the number of holes in a 360-degree bolt circle. By simply putting that Q4 in there, it's going to tap all 4 of the holes. How nooky is that? Now, one little footnote for you: if you decide to use G178, the codes are almost the same, but instead of a feed rate, you can put an F of 1, indicating that there's only one lead, and add a J that includes the threads per inch. So in our case, if we put F1J32, it would then basically do an inches per revolution instead of inches per minute, and we wouldn't have to calculate out our feed rate. Let's see how that looks, shall we? Select and quit, save it, and we'll come back up to our main operating screen. Let's go back to our animated simulation, turn on the program. We'll do where to go? Whoops, I'm not in automatic mode. That would be a problem. Now that I'm in auto, I should be able to restart at N5. Make sure I am graphics in effect. Zip. There's my holes. Oh, I meant to turn off the trace. There we go. Now let's do sequence restart. The turret's enabled, and here comes our rigid tap. Now, a couple of notes about rigid tap on Okuma cycles. It's really neat. If I were to hit feed hold in the middle of the tapping cycle, did you notice that the machine did not stop? It also did not continue to the bottom of the hole like some of the other brand machines. If you hit feed hold when you're in a tapping cycle across the board with Okumas, it'll automatically reverse that tool, pull it out of the hole, and then stop. And when I resume by hitting cycle start, it'll just start the process over again. Some of the other machines, if you look up and you notice that, oh, I made a mistake, it's going to go too deep, and you hit feed hold, it says, you know what, forget you. I'm going to wait until I get to the bottom of the hole. Well, the bottom of the hole isn't deep enough, so you just broke a tap. But at any time during the rigid tap cycle, if I hit feed hold, the tap turns around and backs out. That's a really cool feature I use an awful lot. All right, and then we go home and we're in M1 stop. That's reset. Now we'll go on to the next process. And by calling up our process sheet, we'll see that after face tap, we're going to do the face contour. This is one of the most handy cycles that the C-axis machine has, and probably because of that, it is probably one of the more difficult cycles to explain. So let's see how well I can do with this. I'm going to copy over the live tooling call up and bring it down to where it belongs and paste it. I don't remember what the tool number is, so let's call up our tool list and find that our live Z half-inch end mill is tool number 9. Let's change this up to be 9 by 9, tool 9. 9, 9. We're doing 6 digits here because we're going to expect this thing to be able to compensate for the diameter of the tool. So we will call this half-inch E-mill, M8, M110, and let's give this a nice robust 4,500 RPM. That should be fine for a real nice wicked tool like this. Okay, here's an extra code that we have not used yet. I want to shift the machine from the plane that it's normally in. The working plane on a normal 2-axis lathe is X and Z. We already have figured that out. But I need to shift this into a plane where I'm speaking to it in X and Y terms, which is G17. I believe we have that on our G-code list. Oop, I'll add it by the time you get there. G17 is XY, G18 is XZ, and G19 is YZ. It's pretty much standard for CNC machines across the board, but the two that I remember most are G17 and G18 because those two are the ones I use most frequently. Okay, I'm going to get rid of this positioning move because I want to talk a little bit about what we are about to do. The process that we're going to use is, it seems complicated, but the machine wants to work with us in terms of how to speak to it. I can't possibly expect to be understood if I try to say, hey, I want you to make this hex and I want you to rotate the C-axis to synthesize a Y. That's just way too confusing. So what the builders have put in here is a cycle that will allow us to talk to the machine in coordinates of X and Y, and the machine will respond by moving the X-axis and the C-axis to synthesize this. So here's our hex, which by the print is 1,3. What did we decide it was? Let's find my front M print. There it is. So it's 1,350 across the flats. There's no trigonometry help on this machine, I still went and drew up a hex that's 1/350 across the flats so that I could find each individual corner. That's about the hardest part of my job when it comes to running this particular cycle, is finding those points to point. Now you'll also notice that this is x 675, that's x minus 675, so 1/350, but it's not speaking in diametrical values anymore. Okuma knows that that can be a little confusing, so once we shift into this magic milling mode, it is going to automatically reduce the x-axis to a radial value so it matches the y. That it may seem a little confusing, or why do you do that? But once you start milling, oh yeah, okay, gotcha. I don't have to remember that even though this is x positive 675, I don't have to go and double it because of it being a diametrical value. Nope, it's just a plain old mill. So we will, the reason I launched into that big old segment is because the first thing I want to do is to move to a clearance position, as we've always done, but this one is going to be a diametrical value because we haven't shifted into milling mode yet, or what they call coordinate conversion. I don't want my use of the term milling mode to get confused with M110, which is of course milling mode. So instead of calling this milling mode, I'm going to call this coordinate conversion mode. So I want to make a move that's expressed as a diametrical value because we're not in coordinate conversion mode yet. I'm just going to move to a nice safe distance, a good 3 inches off the part. And we'll go ahead and zero out our C, although that's not required. I just like doing it. And we'll move to a Z clearance plane that's up above the top of the part. Now we will see when I go to graphically verify this that this Z move is critical because the machine is going to make some pretty funky moves when we engage this coordinate conversion mode. And so I want to make sure that I'm well above the part. I added an extra 150 thousandths there just so that, hey, all right, I can be nice and clear. So now I am sitting above the part and I'm ready to start milling. Spindle speed is turning, and I'm first move, I want to express to the machine that, hey, I want to engage that fancy coordinate conversion cycle that Charlie's been talking about, G137. I do have an explanation of this right on top, and we did everything we did to engage coordinate conversion mode, and then we're going to program the profile in X and Y coordinates, mindful that X is now a radial move. And if you are making a G1 move, it will now be G101. If you're making a G2 move, it will now be G102, G103. So we're just going to add 10 in front of all of our G1, 2, and 3 motions. And here's a nice explanation of precisely what it's doing. But let's talk about it as it applies to our part. With the G137, I have the opportunity to put a coordinate shift on the feature. I'll demonstrate that once we're done with the entire part, but the way this is currently drawn, corners are right at the X0, which is very, very handy. Well, if this were rotated, say 60 degrees, now these points are much harder to calculate. So this global shift that can be put in with the G137 would allow me to program as if it were oriented the way you see it, but it would output it shifted by a certain amount. I know, confusing. It'll make sense here in a little bit, so stick with me. I'm just going to currently say that my shift value is 0. So X is going to remain X0 and not shift. Now I'm in coordinate conversion, and I am ready to take the tool from where it is now, which is somewhere out up over the wild blue yonder, and I'm going to feed it to where I want to start the cut. Not touching the part, because as I described a few minutes ago, G137 is going to cause some pretty strange motion to occur as the machine moves its axes to synthesize what we want. So my first move, G101, is a clearance move, and I'm going to put it to X, let's give it 10 thousandths. Basically what I'm wanting to do here is I'm going to position the tool up above the part up here. But I don't want to put it right on X0 because I want to engage cutter compensation, and anytime you're engaging cutter comp in a milling cutter on an Okuma, it's always best to express both axes that are being comped at the same time. If you don't do that, you have the possibility that the one axis that is moving will be comped, the second axis will not be comped until after it makes contact with the part. And when programming by hand, I just don't want to take that chance. So X.01, and let's take this to Y 1.5. I know this is a radial value now, so maybe I should go a little less than that to like 1.4. And so it will have moved off of the clearance position, will have moved into a radial engagement, and I'm going to give it a big high feed rate because again we're just positioning. At this point I think somebody should probably pipe up and say, hey, wait a second, if you're positioning, why did you choose to do a fast feed 150 in a G101? Why didn't you just G0 out there? The reason behind that is that the G137 can cycle does not want to do any rapid moves. It knows that, hey, you may be able to tell me to G0, X1, Y2, and in theory that's easy, but I have to move this rotary axis like crazy to make that happen. So the rule is that when you're in G137, there are no G0s. Don't use it. It will alarm out. So you want to use, if it's a positioning move, just use G101 and make sure that your feed rate is good and high so it will it'll move at a good clip. Now I can G1 to Z minus, let's go 250 so it's past that lip. Oh goodness, now somebody's got to holler and say, wait a second, how come you use G101 here and G1 here? Well, G101 is defined as coordinate replacement. I'm speaking to it in X and Y, but it's going to respond in X and C. So they want G101. There is no axis replacement for Z. It's still going to move in Z, just as described. So Z, when by itself, will be G1. We're not expecting it to replace that axis. Woo, clear as mud, right? Now we'll shift back into G101. I'm going to engage my cutter compensation on this line because we're about to move into the part. And I'll tell it to go to this point right here, which is X0 by Y 0.7794, and give it a feed rate of say 35 inches per minute. By the way, even though this is coordinate conversion, it is going to be moving so that the tool is achieving 35 inches a minute. So it's going to move the C axis faster or slower than the mating axis X, so that it achieves a surface tool footage of 35 inches a minute. And also you notice that I went right to this coordinate, even though we know that's the center of a half-inch tool. Don't try to overthink it and add, a quarter inch to that, because we've already done that in our tool setup, and G41 is compensating for that edge of the tool. So now let's just go through, and I don't have to repeat G101 because it's modal right here, and I'll just go through and name each individual point as we go through. X.675 by Y 0.3897. Next move will be X.675. That was modal. I didn't really have to repeat it. In fact, let's not even put it in there. Let's save a little space. Minus 0.3897. Then we'll go back to X0 by Y minus 0.7794. x minus 0.675 by y minus 3897. Our x is still going to remain 675, so now we're going to go to y positive 0.3897. And our final move is going to be back to x0 by y 0.7794. Now let's get the heck off of the part, and I'm going to go back to where I started, this value right here, with the G40 to cancel the comp, x 0.01 by y 1.4. Now I will have moved well off the part and canceled my cutter compensation. So now I'll go to a z of 0.25, and let's give that a fast feed. We'll just get it the heck out of the way. So now I'm completely done with this cycle, and I'm ready to cancel the coordinate conversion mode. That's with G136. Now we're back to a normal x diametrical value, and c is a decimal degree instead of the calculation it's supposed to make. Let's do a rapid to get the heck away from the part, 0.5, just to say I did, and we'll shut off our tool. I'm now out of milling mode. C-axis is disconnected. I'm going to put in a G18 to return the active plane to XZ, and now G0, X30, Z10, and M1. Want to see how we did? Save that, bring this up, turn on our program. Now I'll warn you ahead of time that when we do this, you're going to see the same feature that we witnessed during the drilling cycle, in that the part is not going to move. It will walk the tool around it, but at least we'll be able to see that our part is correct, and then we'll run over into the machine and I'll show you how it works. So there's our restart. Tool comes in, makes cut up the side. Looking pretty good. Boom. Alright, so now that we've seen what it looks like in graphics, let's go ahead and flip over and see what it looks like in the machine, where the material's actually moving instead of just the part. So let's run over to my collision avoidance, and once again I'm going to find the happy angle. And that should be enough, and we'll move this over, up, and zoom just a bit. And well, let's do just a wee bit. There we go, nice and centered. And now we will run through the process on super speed. Okay, now we're ready to do our milling process. I'm going to slow this down so that we can talk while it's doing it. Let's slow it way down. Now here comes my tool. Notice the motion that it's making while I'm up in the air. This is that positioning move that I described as being pretty funky, how the tool dipped in and then dipped back out. So that's why I always start far away from the part and up above, so it'll do that funky move before it comes into the part. Now you notice how it's, even though we wrote X and Y, it's reacting in X and C and making our part exactly the way we wanted it. Okay, so now we've seen how the machine does it. There's one more thing I want to show you, and this is regarding that C shift pattern that we saw. So we see that these flats are currently oriented so that two of the holes, in fact, let's do a little facing action so that we can look right down the face of the part. Two of the holes were oriented right along the flat of the part. Where'd my material go? Shoop. There's my material. Why is it running the part off tool? I did a boo-boo all over again. That's it, I'm fired. Okay, so 2 of the holes were oriented along the flats and 2 of them were oriented at the points. So what I wanted to show you was that the hex pattern was easy for us to program when it was oriented the way we just saw. But let's say, for instance, that that hex is supposed to be clocked to the holes and have it offset by, oh, I don't know, let's say, let's give it like 30 degrees. So we'll change this to be C of 30. And now let's go in here, turn on our program, and do a sequence restart at N9. Let it buzz through the quick stuff. Okay, there's our holes. There's the tapping action. All right, so now we're going to restart it. And recall that the flat used to be oriented here with points here and here that coincided with the holes. Now that I've added a 30-degree shift, zoop, now you notice it's off ever so slightly. It's no longer set exactly where it was. Now the points are that used to be aligned along here are now aligned up here. It probably would be a little easier to understand if I did a 15-degree, but I think you get it. We can shift the C-axis based on where the grid is, just to make it logical for us to program in a certain fashion. So let's change this back to C0 since our print is calling that out. And I believe we are ready to save this. And now we can move on to our final process, which is drilling the outside holes. Okay, so now we're back to our final process before we do the cutoff. And there we go, the side drill. Let's take a look at our print and see what we've got called out. 1 3/4 inches from the face of the part. We're going to have 1/4 inch by 1/4 inch, 90 degrees from each other, and we're fortunate enough to have them oriented on the quadrant. So let's do this. I'm going to call up the copy over my tool call. Copy, 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 copy. And bring it down to the bottom and paste it. Soup. And we'll change our sequence numbers we have all along. 1111. Whoops, one more. And this is now an X-axis live drill of 250. And obviously X 1 inch is no longer going to be satisfactory. So let's go. Let's give it a good clearance all the way out above the raw stock of the part. And I'm still going to go to the Z clearance plane just so that I can see that the tool is gauged properly. You know, that's pretty much a running theme for me here. And now after that's done, I'll go to my Z location just to kind of position things. And now I don't want to start pecking all the way out at 3 inches, so let's drop this down to 750. Now we're ready for our X-axis peck drilling cycle. Here is a really neat feature that Okuma has done for us. The peck drilling cycle that we used for the Z-axis and the peck drilling cycle that we used for the X-axis is exactly the same, with one exception. Let's go ahead and get up here and we will copy our G183, the peck drilling cycle, bring it over to our X cycle and paste it. And let's talk about what each one of these do again. Our target point, that should be the since we're pecking in X, we want to change the X target point to be our 2.5 minus 250 per side. So that's going to be X 2 inches. And let's go a little deeper. Let's just go 1.950. So we'll do 25 thousandths deeper. That is a diametrical value because we're not doing a G137. And our Z is, of course, wherever we were, in this case 1.75. C is still 0, but the K that we previously specified is indicating to the machine not just the retract plane as I described in the face drilling cycle, but the letter that's used here is how the machine decides whether you're pecking in X or in Z. I and K are the two hot tickets. Let's see if we can find our G183 cycle. Oops, that's a little too big. And oh, I didn't put the description in there. But if we specify the letter I, it's going to peck in the x-axis as you see it. If you specify K, it knows to peck in the z-axis. So instead of being K.25, we're going to be an I value. And since we don't have that counter bore to dip in, let's just say, oh, I0, which will mean that it's going to start the cycle at the 2.75. Yeah, that's a little much. There we go. So now it'll start 100 thousandths in from that diametrical. The L value is our, we're going to leave that up so it'll short retract all the way in. There's our D, and as we learned with the G184, rather than repeat the process for C90, C180, C270, we'll just do the Q. Throw in a Q value, and now it will now it'll make the four holes equally spaced about 360 degrees. And then now that we're done with the cycle, we'll cancel it. We will let's do a nice turn off the spindle kind of thing, and then we'll get out of C-axis mode, and let's do our G0 X30 Z10 M1. Look good? Let's see how we did. I'm going to get rid of some of these extra carriage returns now that we are, in theory, finished with our 2-axis program. And we'll do our select and quit. Whoops, looks like we're running something. That's a good thing to point out. I'm glad we had this little issue. When I tried to select and quit, I get this error that popped up. This is main program execution, and I'm sure if any of you out there have had control time, you've had this pop up before and it'll make you scratch your head. What in the world's going on? If I look over here and look at my machine, there's not really anything going on that I can tell. Turn on my program and look at this. I'm sitting at an optional stop. So the control is currently processing something, whether it's the leftovers of an MDI command or the program is still sitting, even though the machine wasn't moving. The control was still executing a program. So when you try to select and quit, it's telling you exactly that. Your main program is currently executing. So all you got to do is make sure that the machine isn't physically doing something. Reach up and hit the reset button, and now we can select and quit. Boom, no problem. Alright, let's turn on our program. Let's find our restart. We're going to skip to N11. Make sure that our graphics are turned on. Okay. Do our restart. Now the x-axis is here, and I won't beat that dead horse, but you'll notice right off the bat, oh, look at this. Haha, there's a little issue that came up. This is one that you guys may experience accidentally from time to time, and another fortunate incident that we had. If you read the alarm and it says bad direct use of character, I don't know what that means. It's blinking Z minus 1.75. I can get a description of this alarm when the red bar's on the top of the screen. If I come down to the soft keys, you'll see that right next to the F buttons, you got this little guy that looks like a thought bubble. If you push that one, it will open up the manual right to the alarm manual, and it'll take you right to the page that describes the alarm that's on the screen right now. And here's a little something that not a lot of people know. If you look down at, I'm just going to pick any alarm here. This one will work. If you look at the end of your alarm bar, if you're lucky, there will be a number here. And the number corresponds to the line of the programming or the alarm manual that directly relates to what our problem is. In this particular case, it's giving us a hexadecimal code, which doesn't help, but it's saying program direct use of characters 7A. Well, there's not a 7A in here, so yeah, hexadecimal ASCII code. It's just telling me that illegal symbols are designated. So now we learned that, hey, we can open up the alarm manual by using the little happy bubble, but it says that there's something on this line that's not correct. Z minus 1.75. It looks all good to me, but let's go program, let's open that up, and this is something that you guys may do accidentally when you start getting good at typing at the control. There is a button on, I can't show you the button because I don't have a picture of your keypad, but there is a cap lock button that's right next to, I can't even remember what key it is, but if you look, there is a button on your keypad that's dedicated to caps lock. By default, when you power on the machine, caps lock will be on, and it'll stay on until somebody's typing quickly and winds up inadvertently hitting that caps lock key. So that's exactly what I did. If you notice that Z, oh son of a gun, it's lowercase. That one's upper, that one's lower. So I typed a lowercase z, and the control does not know how to handle a lowercase z. Even if the lowercase were in an operator note, it will say what, I don't know what that is, and generate the alarm. Now that I made it uppercase, we should be all right. So one more thing for you. If you look in this upper, yeah, you guys can see that. I just wanted to make sure that I wasn't cut off. If you look on the upper portion of your control, you'll see that the caps lock is highlighted. And if I take it off, now it's gray. So if you have a piece of code that looks good and you don't understand what's up, first thing I do is look up here and check, make sure caps lock is on. All the time. The only time it ever comes off is if somebody's monkeying around with Windows or they inadvertently hit the key. Okay, so auto mode, let's do this all over again. Our program is showing. Let's do a restart at N11. Okay, let it buzz through. Now some of you may have also noticed that on the previous run, when you're doing the rapid graphics like this, it doesn't change the color of the cut, plus that the hex didn't get cut by the end mill. Sometimes, particularly on milling processes, if the tool is moving too fast, it kind of buzzes over in the graphics. It happens. Don't stress. We saw the tool come out and we know that it's good from when we ran not in restart. Boom. There's our X, Y, and Z. And once again, you saw the tool move around the outside of the part, but we know full well that it's going to do it right. Well, let's take the time to prove it, shall we? I got 30 seconds. Do you? Boom, looks like our part. Now we're going through the part off that was programmed in the 2-axis portion. We already know this works pretty well, but let's go ahead and let it cut all the way off. We'll watch the parts catcher deploy. And almost, there we go. There's our parts catcher. We will chunk the thing all the way down. Make a little angle change so we can see that there's our profile and there's our holes at the quadrants. Everybody's happy. How'd we do? We got a part made.